Hey class, Adam Ward here. I want to walk through the first task in our reactor design exercise. You'll recall from having talked about this in lecture and from the handout provided, we've got two stages here. First is we need to deal with acidity associated with sulfuric acid, and we're going to do that by adding limestone in a CSTR. And then our second task will be to deal with the ferrous iron and get that out of the water column. So for our first task, we started with the given information that we're adding calcium carbonate or limestone. We've got the bulk density, 700 kilograms per cubic meter, and we're given the neutralization reaction that's shown here. And as a rule of practice, anytime we see a chemical equation before we start working with it, we do want to triple check, yes, indeed this is a balanced chemical reaction. So task A here, or the first bit A, calculate the amount of limestone required to neutralize the acid, and we're asked to express that in a variety of units. And so you'll remember this problem from a chemistry class. You've got one reagent and you want to know how much of the other reagent do I need to add. And so what you need to do is get into moles and then use that balanced chemical equation to pivot between the different compounds that are involved. So the given information here was we've got 10 to the minus third equivalents per liter of acidity from our sulfuric acid. So we can start with that concentration, and then we can remember that 1 mole of our sulfuric acid is going to produce 2 equivalents. And why is that? Because it's H2SO4. So when we put this in water, it's going to dissociate and we'll get 2 free hydrogens from it. Now we're in moles of sulfuric acid. We can use our balanced chemical reaction to get into moles of calcium carbonate. And you can see why is that a 1-to-1? Because in the balanced chemical equation, as I'm highlighting in purple, there's an implied 1 in front of both of those. So we can solve that out, and we get 5 times 10 to the minus 4th moles of calcium carbonate per liter. And of course you'll remember that's molarity moles per liter, so we're done with the first set. Now in green, let's work through the equivalents per liter problem. If we start from our molarity of calcium carbonate, 1 mole of calcium carbonate has the ability to neutralize 2 free hydrogen ions. And that's of course that calcium is a 2+ ion, so it can neutralize 2 free hydrogens. And so we find that we need 10 to the minus third equivalents per liter of calcium carbonate. And in purple is sort of how you should interpret this conversion between moles and equivalents. Okay, so with those two done, let's get a little more space to write here, and we've got to now work on getting these from moles into masses. And so what you see me writing here in blue is the process of translating from the chemical compound, calcium carbonate, into its molecular mass. So how many grams does 1 mole of this weigh? So this might look familiar again from chemistry, where we're taking in that first column where it's 1, 1, and 3, the atoms of calcium, atoms of carbon, and atoms of oxygen that are in the molecule. In that second column, I'm using the atomic mass for each of those, and so you can look those up on the periodic table. And so we multiply the atomic mass by how many of each are present, and we find that 1 mole of calcium carbonate weighs just over 100 grams. So that molar mass is key to converting between moles and then masses that we can work with in our problem. So if we start from where we ended on the last slide, the molarity of calcium carbonate that we're planning on, we can use our molar mass to make our way into grams of calcium carbonate. And because we were asked for milligrams per liter, you can see I've added that conversion factor, 1,000 milligrams per gram. And in green, I'm canceling out some units just to double check that everything's working. And by my calculation, we get about 50.04 milligrams of calcium carbonate per liter. So that would be the concentration that's required into our reactor. Similarly, we're asked to estimate how many pounds of calcium carbonate per million gallons. So starting from milligrams per liter, you can see I'm converting grams to pounds, and I'm converting milligrams to grams. And that grams to pounds conversion is not something that you should have memorized. That's something that you could just quickly Google or look up in a unit conversion table in the front of your text. And finally, same with the volumetric measurements. 1 million gallons is just about 4 million liters. Again, that's a conversion that one can look up. And so what we find is we need about 418 pounds of calcium carbonate to treat 1 million gallons of this discharge. All right, part B of the problem asks us, what is the feed rate of the limestone? So in other words, what is the mass per time, or the mass rate in which we need to add this limestone? And we're given 3 different types of units to express this answer. Excuse me. So starting where we left off, 418 pounds per million gallons, and recognizing that we've got a flow of 1 million gallons per day in this problem, we find that we need 418 pounds of calcium carbonate per day. So that's how much limestone is going to have to be added to this reactor on a daily basis. From there, the remainder of these problems are unit conversion. And so here you can see me converting from days on the bottom into hours in the denominator and pounds into kilograms. And again, that's a lookup for that conversion. Cancel units, and we need to add about 7.9 kilograms of limestone per hour. And to get into tons per year, the key conversion to know there, 1 year is 365 days, 1 ton is 2,000 pounds. And so in a year, it's going to take just over 76 tons of limestone to complete this neutralization. Step C, probably the hardest in this task of the problem. We've got a single continuously stirred tank reactor, and we want to know what volume is required to achieve the treatment that we want. We're given the information that in addition to the water coming from the power plant, which I've drawn in black and labeled QP, we're also going to add a slurry that's going to be 40% limestone, 60% water. So I've drawn that in blue. Those things will go into the reactor, and then out of the reactor is going to flow in orange some outflow. And we also know that in the laboratory we used a batch reactor and determined about 2 minutes of contact time to reach 99% removal. So that'll be our design goal for this problem. Now, there are several ways that you can start this, but ultimately with the goal of finding volume, I go back to the residence time equation that we've used a few times in the semester. So the residence time in our reactor is its volume divided by the discharge out. And if you're asking yourself, how did he know to use the discharge out, not the discharge from the plant or the slurry? Remember, we want the amount of the thing divided by the rate at which it's removed. And so the rate that water is removed from the CSTR is that outflowing rate. Okay, so this makes the problem look like we need to find outflowing rate. Well, we know it's the sum of the 2 that go in. One of those in black is 1 million gallons per day. So this problem is really about finding the flow rate associated with the slurry, QS. So to find QS, that doesn't show up in any of the equations, other equations written above. So we've got to start thinking creatively. What else do we know about this problem? And the key to unlocking this one is that we know something about that slurry. Right? From parts A and B, we've already decided that we need to add about 7.9 kilograms of limestone each hour. And we know that the slurry is 40% by mass of limestone. So we can use that knowledge, and so I've underlined it in yellow up in the problem statement and highlighted that relationship in yellow toward the bottom of the slide. We can use that relationship to find out that the mass rate of the slurry needs to be about 19.75 kilograms per hour. So the slurry itself, 19.75 kilograms per hour. We're not quite done there. That's a mass rate, but we would need a volumetric rate. And so we're going to continue to analyze that slurry. We recognize that 60% of it must be coming in the form of water. And so we can calculate in purple here, the mass rate of water is about 11.85 kilograms per hour. So at this point, hopefully you're acknowledging or recognizing we want volumetric flow rates, right? Those Qs, volume per time. We're talking about mass rates, mass per time. So now we've got to ask ourselves, how are volume and mass related to one another? And the fundamental property that we're after here is density. Right? That's the relationship or the pivot between mass and volume units. And we can use that knowledge to prove to ourselves that volumetric discharge is equal to mass rate divided by density. How did I get there? We could rearrange that previous equation by dividing both sides by time. So we know that volume could be expressed as mass over density. Volume per time could be mass per time times 1 over density, or Q equals mass rate over density. All right, so with that in our minds, we know that the flow rate of the slurry is the volumetric flow rate of limestone plus the volumetric flow rate of water. We can use our newfound definitions to express those volumetric flow rates based on mass rates and on densities, as I'm writing in black here. And with apologies for my writing overlapping itself just a touch, you can see what I've done is plug in the mass rate for limestone and its density in the left-hand term, the mass rate and density for water in the second term. And if we solve that problem, we find that the slurry is about 0.002 cubic meters per hour. And I'm going to go ahead and convert that into some units that are more aligned with the rest of our problem. So hours into days and cubic meters into gallons. And what we find is that that slurry represents about 139 gallons per day into our reactor. And just to remind you, that's not what we're really after here. We wanted the volume in the first place. So now we can go back to that initial approach we had, residence time equals volume over the volumetric flow rate out, and we can set up a solvable equation. So we wanted a contact time of 2 minutes, and I'm converting that into units of days on the left-hand side. And on the right, we've got our volume divided by Q out. And notice I've got 1,139 gallons. That's the flow from the power plant and the volumetric flow rate of the slurry combined. We can solve that equation, and for part C, we end up with an ultimate solution here of a volume of about 1,390 gallons for that CSTR. And despite my having planned ahead and given myself more space, I didn't use it. Sorry about that. And finally, part D. We are interested in this portion of the problem in estimating a value for the rate coefficient K. And so we're told here, assume that this follows first order kinetics, and relate concentrations, times, and determine K. So for our continuously stirred tank reactor, or for our batch reactor that we used, in the laboratory setting where we got that removal rate, we know that we can describe the time series of concentration using this exponential equation. So 1% of the remaining mass on the left-hand side, because 99% was removed, is equal to the original mass, 1 times e to the minus k t, and in this case we know 99% removal is associated with 2 minutes of contact time. Now we can solve that equation and find a rate coefficient of about 2.3 per minute. So 2.3 divided by minutes is our rate coefficient k. Alright, so all of that work being done, we've done task 1 of this problem. We now have a functional design for a CSTR that will neutralize the sulfuric acid that we need to release from our power plant. You've got mass rates of limestone, you've got flow rates of water, so we would be in good shape now to consider that piece designed. There'll be a follow-up video here where I look at task 2, which is about treatment of the ferrous iron by oxidizing it in the solution. To solve this problem, you had to remember tasks and skill sets from chemistry, including concepts like pH, equivalence, stoichiometry. You had to remember conservation of mass through the CSTR design type equations, the concept of residence time in a system, and how to relate first order kinetics to concentrations. So the first 4 portions of this problem brought to bear both previous coursework and the skills that we've worked on so far this semester. So thanks for sticking with me, everybody, and I'll see you back here for task 2 soon. Thank you.